Today, we embark on an amazing journey through space and time. Imagine a galaxy billions of kilometers away from Earth, nestled between the Milky Way and Andromeda galaxy. Imagine yourself surrounded by an infinite void, but bound by the invisible threads of time. But what is spacetime, and how does it shape the universe as we know it? Join us as we unravel the mysteries of this cosmic web, delve into the complex geometry of space, and explore its dynamic forces. From the emptiness of intergalactic space to the stunning beauty of distant galaxies, we will venture into the unknown and witness the wonders of the universe. So are you ready to embark on this fascinating odyssey? Don't forget to share your thoughts in the comments below. What secrets of space would you like to learn next? If you are as passionate about space as we are, click this subscribe button and join our community of space explorers. Imagine the universe as a calm, still network, like a quiet river flowing between the stars. But it is not entirely inactive. If we were to speed up time, we would see it change subtly and take everything away. Stars, clouds of gas, and even space-time in the form of invisible dark matter are all spinning toward them. For billions of years, our galaxy, the Milky Way, and its neighbor Andromeda have been moving closer together. Eventually, they will collide and merge into one large galaxy. But when that happens, most galaxies actually break apart. The universe stretches like a vast fabric. Galaxies ride these expansion waves, moving away from each other. As they do, their light stretches and reddens, a sign of an ever-accelerating universe fueled by mysterious dark energy. Around 8 billion years ago, the universe began in a cataclysmic event known as the Big Bang. In an instant, it expanded from an unimaginably tiny dot to astronomical proportions. But what caused this big explosion remains a mystery. From these primordial objects, matter clumped together to form filaments, clusters, galaxies, and stars. It is the story of small changes that create large cosmic structures. Our home, Earth, dances around one of these stars, the Sun. Not only is it here, there are planets, asteroids, and comets orbiting in space. The Sun's immense gravity creates a cosmic current that bends the fabric of spacetime and directs everything toward it. This is how the planets orbit. They don't fly into space, they're really making progress. But time around the Sun is pulled back like a cosmic magnet. Even the Moon and our moons are caught in this cosmic dance, orbited by Earth's gravitational pull. Away from massive objects like stars, it flows slowly at times and objects can easily escape its grasp. But as you get closer to a larger body like the Sun or Earth, space-time starts to compress and pull things along even faster. Therefore, rockets must reach incredible speeds to escape ground speed. This is why we experience waves on Earth. Just as the Moon's gravitational pull on our planet causes the oceans to rise and fall, the Earth's rotation affects space-time, pulling it like a cosmic storm. When you throw an apple, even though it doesn't touch the ground, the rotation of the Earth affects it from a distance, changing its path. Deep inside the Earth, space-time descends, trying to pull everything to the center. But Earth materials resist this pull and push back hard. So when we jump back down to the ground, it gives us a boost. At the core, where all power is united, if something can withstand incredible pressure, it would still be perfect. As you move toward the center, all the particles that make up spacetime move forward, bouncing off each other, until they eventually emerge on the other side of the Earth. If we somehow manage to jump off the planet, we're going in the opposite direction. In about 5 billion years, our Sun will reach the end of its life. It will not be able to sustain its pressure and will be pulled into spacetime. The core will disintegrate, creating a super-dense white quaternary, with the outer layers becoming a giant planetary core. But not all stars turn out that way. Somewhere far away there is a superstar 20 times the size of the Sun, and its end is near. Its core collapses and the outer layers explode in a spectacular supernova. Eventually, the core collapses into a small neutron star, placing two solar masses within 30 kilometers of each other. The gravitational pull of the cosmic web is so strong that even light is attracted, causing strange optical effects. Thousands of light-years away, a massive star is about to explode. Some black holes are born near other stars and orbit around them, asking for their stuff. This plasma creates a spinning disk, losing energy as it spirals toward the edge of the black hole. Closer to the center, the flow accelerates infinitely, tearing apart everything in its path. The network is so stretched that it separates the atoms and turns everything into spaghetti at the center. Our current theories cannot fully explain how space behaves at the quantum level in the universe. Nothing stops. When stars die, they mostly spin, collapsing at their cores to become black holes. Their rotation is like an ice skater pulled by their arms. This rotation is imprinted in spacetime, which continues to rotate. Below a certain distance within the black hole's ergosphere, the entire network is pulled into a faster-than-light vortex, pulling everything in its direction of rotation. Even light is deflected around a black hole below the horizon, where matter is falling faster than light. Such a black hole may have a second horizon, where its periodic rotation fights gravity and slows its fall. So there you have it. Black holes, space monsters, continue to amaze us with their mysteries. From their deepest depths to their amalgamation, they form the fabric of our universe. But the story does not end there. Thanks to groundbreaking discoveries like gravitational waves, we are looking deeper into space than ever before. How are you? You are part of this amazing journey. By sticking with our channel, you dive headfirst into the wonders of space science. Together we unravel the mysteries of black holes, explore the mysteries of the universe, and explore the limits of human knowledge. So if you are as passionate about space as we are, click the subscribe button. A central university is an education in this field. Development, artificial intelligence, business and analytics, paid internships and work at partner companies. Enter Central University, a university for future leaders of the IT and business world. 2,500,000 years ago, Andromeda Galaxy. Not far from the center of the galaxy, a giant star is dying. Its final seconds are followed by a tragic explosion. 1 trillion tons of red-hot plasma explodes in a huge cloud, turning nearby planets and moons to dust. A powerful electromagnetic pulse pierces space in all directions. Millions of years later, it will reach Earth. 1885. Earth. The attention of all astronomers on the planet is focused on this amazing astronomical event. The brightest flash in the Andromeda Nebula briefly highlights the nearest lights with its brightness. This amazing supernova is named S Andromeda, and its anomalous parameters have long puzzled astronomers. But after 6 months, the star quickly dimmed. It soon disappears from heaven forever. Unfortunately, at the time of the flash, generally accepted ideas about the structure of the universe were far from modern. In those days, astronomers couldn't measure the distance to celestial bodies, so the bright spot in the constellation Andromeda, also known as Object M31, reflected a simple nebula at the edge of the Milky Way. At the same time, the emergence of new, more powerful telescopes and the development of space technology gradually changed the situation. In the 1920s, observations by Edwin Hubble and other astronomers proved that the Andromeda Nebula is another galaxy like the Milky Way. About a century has passed since then, and science has advanced a lot in that time. The Andromeda Galaxy is known to have a spiral structure and contain approximately 1 trillion stars. However, it is more than 150,000 light-years in diameter and has a relatively small mass, ranging from 800 billion to 1.5 trillion solar masses, about the same as the Milky Way. This is thought to be due to the abundance of red dwarfs and the dark matter in their composition. Like all spiral galaxies, Andromeda has a massive core at its center, made up of millions of densely packed stars. Its light is so bright that it overwhelms observational instruments, making it impossible to distinguish individual lights. For this reason, the remnants of the 1885 supernova, known as S Andromeda, were not discovered for a long time, even though the surviving records clearly indicate that it exploded near the galactic center. Only in 1988, 103 years after the legendary outburst, a small mound was discovered a short distance from the center, a dark spot that stood out against the background of the dark center. Through spectral analysis and modeling of its motion, it was possible to reliably confirm its presence as an Andromeda remnant. This cosmic object was the first supernova discovered outside the Milky Way. Looking closely at Andromeda's core, it's easy to see how it's uniquely different from other spiral galaxies. This is an unusual binary core, the origin of which is still not fully understood. The brighter and wider part is a giant supercluster of many bright stars located slightly away from the geometric center of the galaxy and about 7 light-years in size. The second part, however, closer to the center, is noticeably darker and smaller. Its diameter is about 1.3 light-years. This region is believed to be hidden inside a supermassive black hole 50 million times more massive than the Sun. The nature of such a strange phenomenon remains a topic of scientific debate. According to some speculations, in the distant past, M31 absorbed and dispersed a very large companion galaxy. The bright area is the remnant of its core. Other hypotheses suggest that Andromeda's core still has a single structure. However, it separates with opaque dust, creating an unusual optical effect. Because of the galaxy's remoteness and inhospitality in space, it is impossible to collect enough data to confirm one or the other hypothesis. Meanwhile, by continuing to walk through the central region of Andromeda, you can see one of the most mysterious objects in this galaxy. You can read its complicated name on your screens. The main feature of this celestial body is that it is almost impossible to see even with the most powerful optical telescope. However, when you use X-rays, everything changes. In this part of the spectrum, this light is the brightest point in the galaxy. Observations show that the object is a system of 2 components, one of which is a low-mass neutron star. Its radius is only a few tens of kilometers, and a complete revolution around its axis takes 3 seconds. The second luminary in the system, larger but relatively dim, is probably a red giant. Calculations show that the total mass of the 2 components does not exceed 3 solar masses, and the distance between them is very small. Every 4 hours, a neutron star is captured by its star, so its radiation power drops sharply, then returns to its previous values. Also, due to the small distance between the luminaries, the neutron star gradually absorbs its companion, thus constantly increasing its mass. According to calculations, this process will last tens of millions of years. Eventually, the second light will be disrupted by the tidal force and become a bright and hot ring dome. At the same time, this spectacular object is one of the many lights that tightly surround the center of Andromeda. Together, they form a large scale about 12,000 light-years in diameter, which has a remarkably elongated shape. There is also the announced M31, but it is narrowly oriented to us and is almost invisible from Earth. It is estimated to be about 17,000 light-years long and about 6,500 light-years wide. Overall, the central part of the Andromeda galaxy makes up about 30% of its mass. As we get farther and farther away, we see that the edge serves as the base for 2 giant spiral arms, the majestic coils that encompass the galactic center. At the same time, there are dark gaps between them, the width of which is greater than the Milky Way, and it reaches 13,000 light-years. Calculations show that Andromeda's arms contain 56% of the galaxy's stellar mass, as well as some dark matter. Under the influence of gravity, dust and gas are concentrated in the arms of stars, forming star formation regions. Over time, these gas-dust clouds form into scattered clusters and associations that contain young stars. Their light is reflected and scattered by the cosmic cloud, allowing the galactic disk to glow with fantastic color. One of these clusters is home to a super-bright star called AE Andromeda. It is one of the brightest stars in the galaxy and is a hot blue giant whose luminosity varies with no visible signs. Such things are called clear blue changes and are very rare. Currently, only a few dozen of these lights are known. Due to the high temperature and pressure, the outer layers of A and Andromeda are always in a state of unstable equilibrium. Processes in a star's interior are largely chaotic and unpredictable. From time to time, the red-hot plasma streams collide with each other, creating the brightest lights, changing the brightness of the object by tens of times. Hypothetically, the most powerful of them could increase the brightness of the star by several million times. Such a phenomenon is called a pseudo-supernova and can happen at any moment. Measuring the parameters of such an unstable star, combined with its great distance, is a very difficult task. Nevertheless, modern ultra-precision telescopes have determined that Andromeda's mass is within 50 to 120 solar masses, and that the peak radius of the pulsation is about 55 times the radius of our star, which is only slightly less than the orbit of Mercury. In this case, its surface temperature is about 20,000 Kelvin, and its brightness is 700,000 times higher than the Sun. Like all blue giants, A Andromeda produces the strongest stellar wind, estimated to reach speeds of up to 100 kilometers per second. Therefore, the object loses about 2 quadrillion tons of matter per second. This means that its mass is decreasing every year by an amount similar to that of 10 Earth-like planets. However, for such a big star, it's almost imperceptible. In fact, AI Andromeda completes its evolution faster by losing at least 1/10 of its mass from the stellar wind. The fact is that even though 2 million years is small by cosmic standards, AI Andromeda has passed most of its life cycle. It is estimated that within the next million years the luminary will explode in a supernova, leaving behind a black hole surrounded by a giant cloud of gas and dust. When we talk about the age of stars, we do not take into account that they are not evenly distributed throughout the galaxy. So we can look into Andromeda's past and see how it came to be. The oldest stars, about 13 billion years old, are concentrated in the central part of the galaxy. In contrast, the disk and spiral arms contain mostly young light bodies that formed 4 billion years ago. Many young stars born several million years ago are also located here in multi-star cradles. Hence, in the early stages of its evolution, M31 was smaller in size and more elliptical in shape. By analyzing the parameters of individual Andromeda lights, we can define such an important but at the same time common concept as the habitable zone of the galaxy. The concentration of stars in Andromeda's core, as well as the high radiation and unstable orbits of potential exoplanets, are thought to make this zone inhospitable for the origin of life. Meanwhile, distant planetary systems located on the fringes of the galaxy are poor in heavy elements, resulting in a lack of Earth-like rocky planets. Therefore, only the intervening region of the galaxy can be considered hypothetically habitable. In such a zone, a few tens of thousands of light-years from the center of the galaxy, there is a small dark object called Mega ML7. It represents a red giant whose mass is relatively small and is about 50% of the mass of the Sun. In 1999, thanks to a lucky coincidence, astronomers were able to record the phenomenon of microlensing, during which they were able to study in detail such a unique and distant cosmic body. The measurement was able to determine the mass and spectrum of the light, as well as its surface temperature, about 3,700 Kelvin. But the most important observation is the rhythmic deviation of the star's trajectory from its main direction of motion. Such changes suggest that the luminary may have a fairly massive companion. The object in question is called Mega ML7b and is now considered a potential exoplanet. If confirmed, it would be the first astronomical exoplanet discovered outside the Milky Way. Little is known about this object, but calculations suggest that it is most likely a gas giant with a mass of about 3 Jupiterian. There is information that the diversity of chemical elements, this system is probably not inferior to ours. So the possibility of meeting within the most diverse types of planets is high. Not only gas giants, but also rocky celestial bodies that resemble Earth. Another feature catches the eye when observing the Andromeda galaxy. These are multi-star clusters and associations, far more numerous than the Milky Way. In total, about 460 globular star clusters and about 10,000 are known in M31, as well as several dozen large star associations. Some of them are concentrated in the center of the galaxy, others are scattered in the halo, and others are located in its spiral arms. One of the largest and most prominent structures is the NGC 206 cluster located at the edge of the galactic disk. Previously, this association was considered a globular cluster, but now, due to its size, it has received a higher status and is called a star association. This region of outer space, with a radius of 200 light-years, contains about 300 bright stars and countless others, with a total mass of about 200,000 suns. Their combined luminosity is so great that the association is visible from Earth in a telescope with the center and arms of the galaxy. According to observations, NGC 206 formed as a result of the merger of at least two large gas-dust clouds separated by a dark band of interstellar dust. One of them is about 10 million years old, and the other is significantly older and formed about 50 million years ago. One giant bulge became a point of attraction for interstellar gas, creating a vast area of star formation. Over time, some of its light will radiate into the surrounding space. The rest form a large globular cluster. M31's disk galaxy has many such formations, and not all of them were originally formed within him. Many large star clusters are believed to be remnants of past great cosmic catastrophes. Andromeda is estimated to have absorbed more than 100 satellite galaxies in total. Some of them disintegrated without a trace. Others turned into a giant star stream. A collision with an object called M32 can be considered the largest. This compact elliptical galaxy is located 17,000 light-years above the disk of Andromeda. Its diameter is about 8,000 light-years, and for such a small size, this galaxy has a fairly high mass, about 1 billion suns. At the center of M32 is a supermassive black hole, 2.5 million times more massive than our star, which is amazing for such a compact object. In fact, M32 is the remnant of a larger galaxy that survived the Great Catastrophe. Data from the Spitzer orbiting telescope show that about 800 million years ago, a large satellite galaxy smashed into Andromeda's disk at high speed, leaving an impressive hole in one of the spiral arms. M32 lost most of its stars in the collision and is unlikely to return to its former appearance. It may be a complete elliptical galaxy or a small spiral galaxy with only the central portion remaining. In addition to M32, Andromeda has about 30 satellite galaxies bound to it by invisible gravitational strings. The brightest and largest of these is M110, which is about 15,000 light-years in diameter. Most of the rest are spherical galaxies and are located 1 million light-years away. Nevertheless, together they form the Andromeda subgroup, which belongs to the local group. Its other members are the Milky Way and its surroundings, as well as the Galactic Triangle and other objects. The constant force of gravity gradually pulls the local group together, causing the Andromeda galaxy to move toward us at a speed of more than 300 kilometers per second. In a few billion years, Andromeda will merge with the Milky Way to form a large elliptical galaxy. The grandiose gravity will shift the lights of the two wanderers, scattering them unexpectedly through space. At this point, our planet will be burned mercilessly by the destructive rays of the dying sun, or completely disappear in the ocean of glowing plasma. It is almost impossible to predict what will happen to humanity. Will we populate other worlds unrecognizably altered by natural conditions? Or will we be lost without a trace? As with ancient species, this question is difficult to answer with certainty.